Welcome students for chemistry lecture, and this is our second lecture. In this lecture we are going to see the explanation of the terms what is conductance or conductivity, rho or specific resistance, and the last term here it is specific conductance. We will see one by one these terms, and these terms are oftenly used in the study of electrochemistry. Here you are very well know what is the electrochemistry. Electrochemistry, it is the branch of physical chemistry. It mainly deals with the transformation of chemical energy into electrical energy and electrical energy into chemical energy. And for the last lecture, we have seen what are the types of conductors: metallic conductors or electronic conductors and electrolytic conductors. What is the nature of these conductors? You are known. Then, when the voltage is applied to the electrodes dipped into an electrolytic solution, ions of the electrolyte move and therefore electric current flows through the electrolytic solution. The ions are deposited on the electrodes is called electrolysis. The power of that electrolytes to conduct electric current is termed as conductance or conductivity. And all the conductors, that means metallic as well as electrolytic, they obeys the Ohm's law. And the statement of the Ohm's law, the current flowing through a conductor is directly proportional to the potential difference across it. The strength of current flowing through a conductor is directly proportional to the potential difference applied across the conductor and is inversely proportional to the resistance. Mathematically, it is written as I, it is equal to Phi by R, where I, it is the current strength in amperes and Phi is the potential difference applied across the conductors in volts, and R, it is the resistance of the conductor in ohms. Under the constant potential difference, the current strength, it becomes equal to 1 by R, and this quantity 1 by R, it is the measure of conductance. That means the capacity of any conductor for the passage of electric current, it is nothing but 1 by R. Here the second definition of conductance, we can say that the reciprocal of the resistance is called conductance, and it is denoted by letter C. In some books it is written or it is denoted by letter G, and G, it is equal to 1 by R. Here conductors, they allows the electric current to pass through them, and examples are metals, aqueous solutions of acids, bases and salts. The unit of conductance is Ohm inverse or Mohs, or it is also called as Siemens. Then again the electrolytic conductance. Here electrolytic conductance occurs when voltage is applied to the electrodes dipped into an electrolyte solution. Ions of the electrolyte move and electric current flows through the electrolytic solution. This power of the electrolyte to conduct electricity is known as conductance or conductivity. Electrolytic solution also obeys Ohm's law. Again, this is the repetition of the slide. Then the value of conductivity increases with temperature and concentration. Remember well, the conductance of any solution, it depends on number of ions present in the solution and temperature of the solution. The conductivity of a solution of water is highly dependent on its concentration of dissolved salts and sometimes other chemical species which tend to ionize in the solution. Then the another term here, the specific resistance, it is denoted by the Greek letter rho, and it is just like a 9 letter in a Marathi. Remember, all of you know the resistance offered by any conductor for the passage of electricity through it is directly proportional to its length L and inversely proportional to the area of cross section A. Thus, resistance R, it is equal to rho into L by A, where L, it is the length of the conductor, A, it is the cross sectional area, and rho, it is the proportionality constant, and it is known as specific resistance. And the value of rho, it depends on material of the conductor. Here, under the condition of when length of the conductor, it is equal to 1 centimeter and area of cross section, it is also equal to, suppose, 1 centimeter square, then the resistance of the conductor, it becomes equal to specific resistance. This is the definition of specific resistance. Then here the another term which is, that is the specific conductivity. And specific conductivity, it is defined as the reciprocal of specific resistance of an electrolyte, and that specific conductivity, it is denoted by Greek letter kappa. Mathematically, kappa, it is equal to 1 by rho. Here, this is the kappa and it is equal to 1 by rho. This is the rho, means specific resistance. Again, as we have seen that we have R, it is equal to rho into L by A. Therefore, rho, it is equal to A by L into R. Therefore, 1 upon rho, that means kappa, and it is equal to L by A into R. For L, it is equal to 1 and area of cross section A, it is equal to 1 square centimeter. Then this factor, it becomes unit, and 1 by R, it is nothing but conductance. Therefore, the specific conductance kappa, it is equal to cell constant into conductance value. And by using this equation, we can determine the specific conductivity. Then the another definition of specific conductivity, suppose this is a container, it contains a unit volume of a electrolytic solution, and this cube, it has length, height and breadth equal to 1 centimeter. That means in this cube we have 1 centimeter cube solution, and the conductance of this 1 cm cube solution, it is also called as the specific conductivity of the solution. And this is the case in case of electrolytic conductors. And when the metallic conductor is there, at that time, that conductor, it should have length 1 centimeter and area of cross section, it is equal to 1 square centimeter. For such a metallic conductor, its conductance, it is equal to specific conductance. And the ratio L by A, it is called as cell constant. The unit of specific conductance is ohm inverse centimeter inverse, and the SI unit of specific conductance is Siemens meter inverse, where S, it is the unit of conductance. Then the next term here, it is equivalent conductance. Equivalent conductance is defined as the conductance of all the ions produced when we dissolve 1 gram equivalent of an electrolyte in a given solution. Or alternatively, we can define the equivalent conductance as it is the specific conductance of 1 gram equivalent of electrolyte. And to understand this, consider this is a rectangular vessel which is made up of metal, and its two sides, they act as a electrodes, and they are connected to the positive terminal of battery and negative terminal of battery. Then suppose we have taken 1 centimeter cube of electrolytic solution in this container, and we measure its conductance. At that time, the conductance measured, it is equal to its specific conductance. And if we add 1 gram equivalent of electrolyte in the 1 cc solution, and then again we measure its conductance, at that time this becomes equivalent conductance according to definition of equivalent conductance, as equivalent conductance is the conductance of all ions produced by 1 gram equivalent of electrolyte in a given solution. Our solution, it is 1 centimeter cube, and we have dissolved 1 gram equivalent of electrolyte. Therefore, as per the definition, equivalent conductance, it is equal to volume of solution into specific conductance. Then here again, as a specific conductance, we have taken 1 centimeter cube of solution. We denote it as a kappa into phi, and phi, it is the volume of the solution. Again, if we add 99 ml or cube of solution, and the added salt, it will remain 1 gram equivalent. We measure the conductance. At that time, equivalent conductance, it is equal to specific conductance into total volume of the solution. Suppose 1 plus 99 means 100 into 100, that is the equivalent conductance. And again, if we have 1000 cc's of solution in this container, at that time equivalent conductance, it is equal to specific conductance into 1000 divided by n, where n, it is the normality, and phi, it is the volume of solution used. Here 1000 cc's, it is the volume of the solution, and n, it is the 1 gram equivalent of solution in 1000 cc's. Therefore, according to this, the unit of equivalent conductance is ohm inverse centimeter square into equivalent inverse. This is the explanation of the equivalent conductance. Remember, in a short, equivalent conductance, it is the product of specific conductance into volume of the solution. As per the definition, then the next term, molar conductance, and the definition molar conductance is defined as the conductance of all the ions produced by ionization of 1 gram mole of an electrolyte when present in phi ml of solution, or it is the specific conductance of 1 mole of electrolyte, and it is denoted by molar conductance lambda m. It is equal to, it is just similar to equivalent conductance. Here kappa into phi, where kappa it is the specific conductance and phi it is the volume. Here this phi is the volume in mLs containing 1 gram mole of electrolyte, and if C is the concentration of the solution in a gram mole per liter, then the molar conductance lambda m it is equal to kappa into 1000 divided by m, and its unit are ohm into centimeter square per mole. Then suppose for example the electrical conductivity of water sample is used as an indicator of how salt free or impurity free the sample is. The purer the water, the lower is the conductivity. For example, solution, suppose we have sea water, its electrical conductivity is 5. Then drinking water, it has 0.005 to 0.5, and deionized water, it is equal to 5.5 into 10 raised to minus 6. Again, in the recapitulation, we summarize all the points once again. Here we have seen the explanation of the terms conductance, or it is also called as conductivity. Then the second term rho, that is specific resistance, and the specific conductance. Here all conductors, they obey Ohm's law, and when we apply the constant voltage in between the two electrodes, at that time the quantity 1 by R, it becomes a measure of electricity conduction. Therefore, the conductance is also defined as the reciprocal of resistance, and it is denoted by either C or G. It is equal to 1 by R. The unit of conductance is ohm inverse or moles, or it is also called as Siemens, represented by capital S letter. Electrolytic conductance, it is nothing but when we apply voltage across the electrodes, then the migration of ions takes place, and by the migration of that ions, current will flow in between the two electrodes. That is the electrolytic conductance. This is the Ohm's law. Again, remember that the value of conductivity increases with temperature as well as with concentration of solution. Then specific resistance. Here the resistance offered by any conductor for the passage of electricity is directly proportional to length L and inversely proportional to cross-sectional area, that is R, it is proportional to L by A, and R it is equal to rho into 1 L by A, where rho it is the specific resistance, and its value depends on material of the conductor. Again, we have seen what is the specific conductivity. In short, specific conductivity is the reciprocal of specific resistance. It is denoted by Greek letter kappa, and it is equal to 1 by rho. This rho, it is in a Marathi we write as a 9. This is the Greek letter rho. And rho it is equal to A by L upon R, where A it is the cross-sectional area, L it is the length of the conductor, and R it is the resistance offered by that conductor. Therefore, we can write the specific conductivity kappa it is equal to L upon A into R. When L and A are unit at that time, the specific conductivity it is equal to conductance of that solution. Then we have seen the equivalent conductance. Equivalent conductance is the conductance of all the ions produced when we dissolve 1 gram equivalent of electrolyte in a given solution, and it is nothing but lambda equivalent. It is equal to product of specific conductance into volume of the solution. Then molar conductance is nothing but the conductance of all the ions produced by ionization of 1 gram mole of electrolyte when present in phi ml of solution. And mathematically it is written as lambda m it is equal to kappa into phi, where again kappa it is the specific conductance and phi is the volume of solution. And this is the example of electric conductivity for seawater, drinking water and deionized water. If you have any doubts, you can ask me and get clear your doubts in understanding these terms. Thank you. Thank you very much.